Hello everyone, I'm Carter and this is going to be step 1, 1994, question 2. So a bit of differentiation here. In my opinion, this is a lot easier than question 1, which you can see my video about if you check the channel. But let's get straight into it. So we need to find the derivative of each of these expressions. And the first one is pretty straightforward. So given that a is constant, differentiate the following expressions with respect to x. Well, the first one is just x to the power of a. Right? So a is a constant, right? So it's something like, for example, if I have a is equal to 4, then it's just x to the 4. And you know that the derivative, I hope you know, if you're saying the step, that the derivative of x to the 4 is equal to 4x cubed, right? So in general, this is just the power rule, the derivative of x to the power of a, you should hopefully know, is a times x to the power of a minus 1. And if you didn't know that, now you do. Okay, so there we go, right? So we have the derivative of x to the a is a times x to the a minus 1. They don't expect anything else from that. They literally just want you to state what it is. Okay, simple. No need to prove anything. Okay. So for the second part of the question, we now need to differentiate a to the x. So this one is a little bit more interesting, although the result is still fairly standard. But if we just have a function, so f of x is equal to a to the x, so that's our function of x, we want to be able to differentiate this function. So before we do that though, what we can do is we can take logs of both sides. So if I have ln, and I'll take natural log, it doesn't actually matter what base it is. I mean, you can typically just use natural logs most of the time. Unless it's a case where it's simpler to not use natural logs, but again, that doesn't matter. You can still probably use natural logs. Anyway, so you have ln of a to the x is equal to ln of f of x. Okay, and I'll call f of x y, just because that's probably easier. So ln of y. And obviously we know from our power rule that we can like bring this x sort of down to the front. So this means that x ln a is equal to ln of y. Okay, so at this point we can use implicit differentiation, which I will assume that you're confident with. If not, go check that out before moving forward. Effectively, at this point, you can use implicit differentiation that you've learned from A level to basically differentiate this, right? So effectively, on the left-hand side, we have just a constant, ln, so because A is a constant, right? ln of A is therefore also going to be a constant, as long as it's defined. Obviously, you can't have the natural log or log of any natural or of any negative number. So as long as it's defined, clearly this is just going to be ln of a is just going to be another constant, right? So it's just like another, it's like a k, right? So effectively what we have is kx equals ln y. So when I differentiate both sides with respect to x, then what are we going to get? Well, clearly on the left hand side we have a linear term, so the derivative of like 4x is just 4, so the derivative of kx is clearly just k. And on the right hand side we have ln, so the derivative of ln of y is going to be just 1 over y multiplied by dy dx. So effectively it's just like a use of the chain rule, right? That's basically how implicit differentiation works, is you differentiate ln of whatever it is as if it was ln x, right? So the derivative of ln x is 1 over x. And so effectively we can treat sort of ln of y the same way. So obviously the derivative of ln of y, at least with respect to y, would be 1 over y. But because it's with respect to x, it's as if we have some, obviously y itself is a function of x. So you take the derivative with respect to y, and then you multiply that by the derivative with respect to x of the thing on the inside. Effectively, it's just a chain rule, right? So like if ln of y was u, then effectively I have that du dx is du dy multiplied by dy dx. This is just the chain rule, right? Let me just zoom out. That's just the chain rule. So obviously du dy, I already know what that is. That's just 1 over y. Dy dx, we don't know what that is because we don't know explicitly. Well, we're trying to find it basically. And so in order to find it, we need to just name it dy dx until we actually know what it is. So we have that k is equal to 1 over y multiplied by dy dx. And so obviously this implies that y multiplied by k is equal to dy dx, right? But clearly k, but what is k? K is just ln of a. So we have that y times ln of a is equal to dy dx. But then what's our y, right? Well, our y, we recall that our y is just a to the power of x. So effectively we know therefore that dy dx is just a to the power of x multiplied by ln of a. And then that completes that part of the question. So for some people that result will be very simple and like you would have already known it. But it's actually the method that you use to get this result which is going to be the most important thing. Because something that's much less standard and pretty much only asked for these types of sort of thought-provoking problems is the derivative of x to the x, right? So the derivative of x to the x is not x times x to the power of x minus 1, because that would be treating x as a constant, but we're actually letting x vary, okay? And it's also not going to be whatever the analog would be as if you're treating it as a to the x, whatever. Like, it's not going to be x to the x times ln x, right? Because again, it's not, x is not a constant. You can't treat it as a to the x, okay? In the cases that we already dealt with, a was a constant, whereas in this case, x is varying. We want to let x vary. We want to find the derivative. So what we actually have to do here, though, is not too dissimilar from what we've already been doing. So effectively, if I just go down, and I have triple I, and I have my function of y, which is x to the x. You can just take natural logs of both sides. So obviously, natural log of x to the x is, you can use the power rule on that. Basically, just gives us x ln of x, right? So whenever so then I can use my implicit differentiation. Obviously, the derivative of the left-hand side we already have from before, 1 over y multiplied by dy dx. And then the derivative of the right-hand side, that is a typical product rule. So if you don't know what the product rule is, go check that out. It's an A-level technique for differentiation, and it's pretty useful. So effectively, we differentiate this thing on the left-hand side and keep the thing on the right-hand side here the same. So we have 1 times ln of x, it's the derivative of x is 1. And then you add this thing multiplied by the derivative of the thing on the right-hand side. So x multiplied by the derivative of ln x, which is 1 over x. So effectively, x times 1 over x, that's going to be 1. So effectively, what we have here is just going to be equal to ln x plus 1. So that's our 1 over y dy dx. To get dy dx, we have to multiply both sides by y. So obviously, that implies that dy dx is equal to y lots of ln x plus 1. And obviously, recall that y is x to the x. So we can just relabel this as x to the power of x multiplied by ln of x plus 1. And that gives us our answer. Okay, and like the next part of the question, now we need to do x to the power of x to the power of x. So it's kind of like a sort of a power tower here, but I mean, really this question is just a repeat, right? Because we basically answering this question is pretty easy now. It's just a repeat of the method that we already used in parts II and triple I. So I mean, really, there's not too much that you're gonna have to. I mean, as long as you see that, there's not too much else that you really need to do here other than just do the differentiation and use the differentiation rules properly. Effectively, if you have that y is equal to x to the power of x to the power of x, right? Well, then you also, what you notice is that when you take ln of y, you're going to get ln of x to the power of x to the power of x. And so effectively, this x to the power of x to the power of x, you can bring this x to the x down. So you have that ln of y is equal to x to the x multiplied by ln of x, and then you can just take the derivative of everything here, right? Because you already know what the derivative of x to the x is. So effectively we get that 1 over y dy times dy dx is equal to the derivative of x to the x, which we have from before, which is x to the x times ln x plus 1. So ln x plus 1, and then obviously you keep the thing, so you take the derivative of the thing on the left-hand side, and you keep the thing on the right-hand side the same. That's just the product rule application. So you're going to be multiplying this by ln of x, and then you're going to add x to the x times the derivative of ln x. So the derivative of ln x is 1 over x, so sorry, times the derivative of ln x. I think I might have said add the derivative of ln x. No, times the derivative of ln x, which is 1 over x. So effectively, this just gives us, so we have x to the x multiplied by ln squared x. So ln squared x I'm going to use to mean ln x squared, basically. I don't think it's standard notation, but I'll write it here. And then plus ln, or maybe what's better actually, we can just say ln x times ln x plus 1, because it's probably just like a bit weird otherwise. Ln x plus 1. The only bad thing about it is the brackets, but it's fine. And then add x to the power of x minus 1, right? Because you're doing x to the power of x divided by x, so you can use your indices sort of rules on that to give you this. But that's only 1 over y times dy dx, so we need to multiply that by y to get our final answer. So this obviously implies that dy dx is equal to y lots of that. And remember that y is just x to the power of x to the power of x, so we just have this is x to the power of x to the power of x multiplied by x to the power of x. Actually, I will write it as ln squared x just because it's a bit neater. Add ln x, or maybe no, instead we'll just write it as ln x squared, because I think some people get mad at me if I do it that way. Ln x squared plus ln x, and then plus x to the power of x minus 1. Okay, and I mean, we can just kind of leave it in that form if you want. I mean, cleaning this up isn't like, I mean, you could in theory like multiply these together, so you get x to the power of x to the power of x plus x, but it's kind of like not, I mean, it's not the cleanest thing, right? So you don't really, you don't really have to do that. I mean, I think you can leave it in this form if you'd like to. Okay, so that's that one. Okay, so moving on then to the last part of the question, we now want to differentiate x to the power of x and then that to the power of x. So instead of obviously like, if I'm doing like 4 to the power of 4 to the power of 4, that's not the same. Actually, sorry, let me just zoom out here as well. That's not the same. That's actually not equal to 4 to the power of 4 to the power of 4, right? Because one of those is like 4 to the power of whatever 4 to the power of 4 is, which is, so this first one is 4 to the power of 256, but the second one is 256 to the power of 4, right? So these things, these are not going to be the same, right? Because 4 to the power of 4 to the power of 4 is going to be like 4 to the 4 times 4 to the 4 times 4 to the 4 times 4 to the 4, right? So you can just say that's 4 to the 16 because those powers are all going to add up. But you can't do that with this case, right? Because it's 4 to the power of 256. And yeah, clearly 4 to the power of 256 is definitely not the same as 4 to the power of 16, right? So those two things are clearly different. So effectively then, for this last part of the question, we need to do sort of x to the x to the power of x. Now, we can relabel that though. So obviously for part V, what we have is we have that our y is equal to x to the power of x to the power of x. So it's like x to the power of x times x to the power of x times x to the power of x, sort of x times. And so effectively what that means is we can do x to the power of x plus x plus x plus x plus x, x times. So we're going to get x to the power of x times x, right? So this is just x to the power of x times x, which is equal to x to the power of x squared. Okay? So this is our sort of clean form here for what's going on. And so all we need to do then is differentiate it. So you just take logs of both sides again, as we've been doing this entire time. So you have ln of x to the power of x squared. That's just equal to x squared multiplied by ln of x. And you can just differentiate. So now we differentiate both sides. You get 1 over y times dy dx is equal to, so product rule again, so we differentiate the thing on the left, you get 2x multiplied by the thing on the right, plus x squared times the derivative of the thing on the right, times the derivative of the thing on the right, I would say plus, which is 1 over x, the derivative of ln x is 1 over x, so we get this is equal to 2x ln x plus x. Okay, and now obviously we can multiply this by y as well, so to get dy dx is equal to y lots of 2x ln x plus x. But remembering that y is just x to the power of x squared, this gives us x to the power of x squared multiplied by 2x ln of x add x, which is our final answer. Very nice. And I want to add that you can actually simplify this a little bit. You could say this is x to the power of x squared plus 1. So you can basically just multiply this through, you can like factor out on x from this expression and then multiply it by x to the power of x squared. So x to the power of x squared times x to the power of 1 is just x to the power of x squared plus 1. And then you can say it's just multiplied by 2 ln x plus 1 if you want, but they're both the same expression. So that's that. Nice stuff.